Okay, and we have, solidarity with our friends in Ukraine. In fact, solidarity with our friends all over the world because the world is a little bit crazy right now. But this is science, and hopefully we can cut through some of the politics. So this is the outline of my talk, and my plan is to go fairly slowly through this because I'm guessing most people aren't familiar with this way of thinking about um, matter. That's a pretty broad statement, but I think I'll make it clear in a bit what I mean by that. And then once one sees this somewhat different perspective on the nature of matter in the condensed phase, then we'll see how this maps onto problems like catalysis, and particularly focusing on enzymes. So I'll be talking about the vibrational Stark effect, which is something that we measured for the first time now quite a number of years ago, just as a really as a side topic, and I'll explain exactly where that came from and why, and tell you a little bit about this type of spectroscopy because it's again not that familiar, and then use that as the basis for talking about catalysis. And what I think is a different view of catalysis. So let me start with the sort of canonical um, figure, which is shown here on the left. And what I mean by canonical is this is a figure taken from an old paper by Wolfenden, a distinguished a mechanistic enzymologist, which really is meant to illustrate just the extraordinary catalytic proficiency of enzymes. This goes way beyond what conventional chemical catalysts, at least most conventional chemical catalysts, can achieve. And of course, chemistry is largely dominated by trying to understand and improve catalysts for a wide range of activities. So we're talking about rate accelerations that aren't just a factor of 2 or a factor of 10. We're talking about things that are 20 orders of magnitude. So big numbers, things that are worth thinking about. We may not get the predictions right within a factor of 2, but if we're talking about 20 orders of magnitude, that's a big deal. So, of course, the way we think about this is shown here, a picture on the right, which is, what we show already in high school chemistry classes. Despite the fact that we really don't know that much about transition states because we don't see them, we kind of imagine them, but we have this idea that the uncatalyzed reaction proceeds with an activation energy, an activation free energy, and in the catalyzed reaction, that activation free energy is lowered. And that picture, is widely accepted, and it's not something that we're challenging here. But the question really is, what is responsible for this lowering of the activation free energy? And that's a very general question. It's a general question in chemistry. It's a general question in biology, and it's not so easy to answer in most cases. There's lots of hand waving and speculation, and of course a lot of calculation, since a lot of these much of this is not readily observable, and that's going to be really the theme of this talk is how do we actually make observations that are relevant to understanding what lowers the activation free energy. So here's that picture again, shown a little bit differently, and now with an emphasis on what we're going to focus on in the rest of this talk, and that is the movement of charge. And of course, charge is always moving in the course of chemical reactions. We're talking about moving nuclei around, we're talking about moving electrons around, and so there is an electrostatic an important electrostatic process happening in the course of any chemical reaction. And I've just made a simple reaction coordinate here, just schematically for the purpose of talking about it, in which we take a reactant which has, let's say, a bond that we're interested in that has a dipole moment. Let's say that dipole moment is 0, just for amusement. And then we're going to move charge in the as we go to the transition state and undergo a reaction. Now, my background is in electron transfer and proton transfer, where it's obvious that you're moving charges. Those are charged particles. But if you think about it, that's really going on in the course of any chemical reaction. There's a movement of charge. And so and we're using a completely classical view here, which is undoubtedly wrong. There's certainly an over approximation. We're going to say that there's a dipole moment in the transition state of some magnitude. We'll call it the dipole moment transition state. And then there's a dipole moment associated with the reactant. And again, when I talk about dipole moments, I'm not talking about molecular dipole moments. I'm talking about the dipole moments of the bonds that are undergoing chemical reactions. And that distinction will become important as you'll see later. So we have a difference dipole going from reactants to transition states, and we'll call that the reaction difference dipole. Okay, again, these are just vector quantities. We're treating them completely classically and undoubtedly oversimplifying. And then the idea is, and again, oversimplifying, that the environment around the reaction, this could be a solvent, or it could be, in the case of an enzyme, the active site of an enzyme, provides an electric field. And we'll see where those fields come from in a few minutes. Let's just talk about it generically now. There's a total field from the protein. Again, we're treating this classically, so we're going to treat it as a vector. We're going to call it F with an arrow above it. And then we have the very simple idea that, again, completely from classical electrostatics, that the effect on the energy of the system is going to be just the dot product of these two vectors. Okay, and that's what's shown here. And this negative sign here is important because we're using the physics convention for dipole moment directions. Chemists, for whatever reason, have the reverse direction, which causes a huge amount of confusion as everything is shifting in the wrong direction. But this is the correct physics definition of this interaction. This is, in fact, how you define fields. So we have this, and now the question is, who cares? Does this, I mean, I can draw a schematic like this. The question is, does it have anything to do with reality? And it's because we don't really know, in the case of an enzyme, for example, what the field is from the protein. It may be large, it may be small, we may be able to perturb it. There's lots of discussion in the literature about electrostatics, sort of in fairly vague terms, but we want to be a little bit more specific here, and it turns out to be important. We can put some numbers on this. This is just a made-up example. If we imagine moving charge by, let's say, 1 angstrom, and that would be not untypical of what goes on in a chemical reaction involving the movement of charge in an individual bond of the sort that I'll be talking about in a minute. These are just numbers to give you a flavor of things. And then imagine that the field were 10 megavolts per centimeter coming from the protein. And let's say it were aligned with the reaction difference dipole. Well, then that would have the effect of lowering the activation free energy by roughly 10 kilojoules per mole. That's not a very big effect, but of course that in the Arrhenius equation that goes into the exponent, and so it's a not trivial effect. But the question is, 10 megavolts per centimeter, is that a big field or a small field? Those aren't units that most people are familiar with, and they're sort of odd units. We should really be using volts per meter, which is the standard unit. And units of electric fields turn out to be a huge source of confusion. We use megavolts per centimeter for reasons that will become clear in a second. And they're the most widely used units. Suffice it to say that 10 megavolts per centimeter turns out to be a very small field, though if you were to make a parallel plate capacitor and apply a field of 10 megavolts per centimeter, you'd get dielectric breakdown. But within, let's say, the active site of an enzyme or within a solvent, the fields are in balance. And so fields of this magnitude are easily achieved. And now going back to our simple equation here, the difference dipole a reaction difference dipole isn't likely to change by much more than an angstrom or 2 or 3 for a typical chemical reaction. But the field, it's just linear in the field, could be much larger. Now, of course, the field has to be aligned with the reaction difference dipole. It could be in the opposite direction. It could raise the activation free energy, or it could be perpendicular, again, in this classical view, in which case it would have no effect. So we can imagine, let's say if the field were 100 megavolts per centimeter, that it would have a very, very large effect on catalysis. And we'll see that fields of that magnitude are in fact found at the active sites of enzymes. So the question then, and this is what I'm going to talk about for the rest of my talk, is really how large is the electrostatic contribution to the catalytic rate? And ultimately then the chemical or biochemical question is the question of design, and that is, could we in principle design electric fields in order to achieve what's illustrated in this picture? Okay? Or maybe nature has, by evolution, come up with that design. And I'll say more about that at the end. So the bottom line here is that we can now measure these local and catalytically relevant electric fields using the vibrational Stark effect. And that's why I'd have nothing to talk about if it weren't for that. Okay, so this is really the most important figure in a way. And if you understand or buy into this concept, then the real question is it true or not? Okay. Now, let me just make a few very general comments before getting into specific details. So people are accustomed to thinking about electrostatics in the context of electrostatic complementarity. So plus attracts minus. That's an obvious and very, very important concept. And that will, of course, affect things like binding constants or inhibition constants in focusing now, let's say, on catalysis in an enzyme. But what we're talking about here is something different. We're talking about another aspect of electrostatics, which we'll call electrostatic activation. That's what I was describing exactly in this hypothetical picture. And that will affect the rate constant for catalysis, or it could affect the on rate for binding. So this now really summarizes the whole thing, and I'll come back at the very end of this talk and hope to have convinced you that this concept of electrostatic catalysis is important. This concept was proposed some time ago by Ariel Warshel, the famous theorist responsible for much of the way we calculate things in complex systems. He won the Nobel Prize for his work on the development of molecular dynamics. And he proposed this sort of importance or emphasized the importance of electrostatics, but was largely, I would say, ignored by most of the enzymatic community who tend to think more in terms of recognition than in terms of activation. And as you'll see, we very much favor or we think this can be a very, very important contribution. Okay, so now let me get into sort of the nitty-gritty of the spectroscopy that is behind all of this, okay, and really how we got into it. So what is Stark spectroscopy? I think everybody has probably at some point or the other learned about Stark spectroscopy because it's the very first problem you learn when you do quantum mechanics and you do perturbation theory. You look at the application of an electric field to the spectroscopic transitions in an atom or molecule. The original experiment by Stark and also independently by Lasorda in Italy was way back in 1813. So I'm sorry, 1913. So we can hardly take credit for this. And it was a key experiment that was completely ununderstood. The results were understood. They were trying to test the Bohr model. It didn't work. And it wasn't until Schrödinger developed what we now call quantum mechanics that the effects that Stark and Lasorda observed could be explained. So that work was done in an external electric field, and I want to make it very clear. We'll be talking about local internal fields and external fields, and we have to keep them clearly distinguished. In this case, we're talking about the effect of an external field. In the case of the Stark experiment, it was done in the gas phase. It's rarely done in the condensed phase. That's something that we've been very much sort of developing the methodology for doing. And what it is simply we apply an external field. Again, we're taking a classical view here. And now the field is coming from let's say, in a parallel plate capacitor. And we have associated with the molecule some spectroscopic transition. This could be an electronic transition, or it could be, as we'll see, a vibrational transition. We'll call that, and what's relevant is for that transition, what is the change in dipole moment going from, let's say, the lowest electronic state to the first electronically excited state, or the lowest vibrational state to the first excited vibrational state. So that's another delta mu, not to be confused with the delta mu we were talking about before with the reaction difference dipole. This is an intrinsic property of the molecule of the probe. Okay, and again, the minus sign is by convention. Okay, and again, it's just a dot product, and so depending on orientation, we'll have a change in the energy. And usually this is for most spectroscopic transitions, this is the effect that matters. This is the first order term. It's linear in the field, and it's called the linear Stark effect, and it's usually what dominates. So the units we use for the probe are it's a dipole moment change, and so we can use the standard units that we teach about in freshman chemistry. For dipoles, we talk about Debye, or an alternative language, and this now will explain our choice of units, is what's called the Stark tuning rate. And the Stark tuning rate has these somewhat bizarre units of wave numbers per megavolt per centimeter. You have to sort of stare at that for a second, and just for precision, 1 dBi is equal to 16.8 wave numbers. So these are isodimensional. But if you look at this, what this says is per unit field, given in megavolts per centimeter, how many wave numbers, the standard unit that spectroscopists use on the horizontal axis in their spectra, how much a spectrum will shift. And that's really why we use megavolts per centimeter, because we have these weird units of wave numbers that are commonly used in spectroscopy, especially in IR and Raman spectroscopy. And we'll see these units playing out over and over. It's just a weird looking unit until you get used to it. What is it really? It really is how sensitive a transition frequency is to electric field. So for a given magnitude of the field, depending on how big this is, the energy will shift to a greater or lesser extent. And so this represents the intrinsic sensitivity of a transition to a field. And the way we do this, just very briefly, is we make a parallel plate capacitor. We have external field. We typically freeze the sample because we don't want the molecules to reorient. They're randomly oriented. The sample is isotropic upon freezing, or we sometimes put these things in polymer films. And then we apply an external field. So we have an absorption spectrum, could be electronic, could be vibrational, shown here schematically in the absence of a field. And then some of the difference dipoles are pointed with the field, some are pointed against the field. Those are the ones that are going to shift the furthest. Those are shown with red and blue populations here. And the most common situation is going to be there are many more ways to be at the equator than at the poles. And so the most common situation is that delta mu for the transition will be perpendicular to the field. And so it won't be affected at all. So we get this distribution because the sample is isotropic, some going up in energy, some going down in energy. And if you just stare at this for a second, you realize that what the effect is going to be is to broaden the band. And in fact, you can show analytically that, not to get too far into the weeds here, but so long as the maximum Stark splitting is less than the inhomogeneous line width for the transition, you can show that the shape you expect is the second derivative of the absorption. That's just a broadened band minus an unbroadened band gives something that looks like a second derivative. Okay, and we can analyze, knowing what the external field is, what the magnitude of this change is, and use that to extract out what the probe sensitivity is. It's not just got a magnitude, but it also, and this is very, very important in what will follow, it also has a direction, okay? And that direction can be obtained by, I'm not going to go into this at all today, by a linear dichroism experiment. In the case of a vibrational transition, that difference dipole, as you might expect, lies along the bond axis of the, let's say for a carbonyl group or for a nitrile, something like that. And therefore we know its direction in its environment just by its molecular structure. So this is an early experiment now showing an electronic Stark experiment. And I'm using this to illustrate really, perhaps not chronologically, but at least logically, what got us into this whole business. We were looking at the transition for a polyene, a carotenoid molecule, in the LH2 complex from photosynthetic bacteria. This is the complex that has been a fever dream for many spectroscopists over the last couple of years, looking at ultra-fast electronic transitions. But this is a very different and simpler experiment. And this was a completely accidental discovery. We were very, very surprised to find here's the absorption of the carotenoid. This is the vibronic structure associated with it. This is this long, skinny molecule. Here it is. It looks exactly like the second derivative of the absorption. And then this is a fancy experiment, which I'm not going to go into, which allows us to look at higher order responses to the field. And they follow rigorously this simple idea of a difference dipole dominating in this case, electronic Stark effect. What was really astounding was that the magnitude of this is huge. And why should that be astounding? Well, first of all, there are very few molecules that have a difference dipole that large. Typical dye molecules of the kind everybody is familiar with, you have a charge transfer transition and it maybe has a difference dipole of a few dBi, but this is very, very large. Furthermore, there should be no difference dipole for this molecule because this molecule has essentially inversion symmetry. It's not exactly inversion symmetry, but it's very close. And in fact, if you take the molecule out of the protein, what you find is that it doesn't have a large difference dipole at all. In fact, what it has is a large polarizability change. And that's been well known for polyenes. It's been very important in the visual pigments, for example. It's been known for a long time. And so you sort of stare at this and you think, well, why in the world would there be a large difference dipole moment in the protein, but not in the absence of the protein? And the inference that we drew at the time, which I think is correct, is that it's the electrostatic field, the organization of charges and polar groups in the protein that induces a large dipole moment in a polarizable chromophore. And then we're just observing that using an external electric field. So it's the field actually intrinsic to the protein. But then you stare at this for a while and you say, well, where is the field exactly? Well, that's not, in other words, that's not a very chemically useful thing because for chemistry, we're interested in what happens at the level of individual bonds. And here, it's not at all obvious where the field is. And so the logical way of getting at the field locally is to look at a local probe. And that's what the vibrational Stark effect is all about. Okay, and that's the logic that I hope to convince you of today. So here, for example, was one of the very first things we looked at a long time ago, just a acetonide trial in a simple glassy matrix. Here's the absorption spectrum, here's the Stark spectrum, and here's a fit to the second derivative, and you can see it fits very, very well to that second derivative. Now, here the difference dipole is much, much smaller. I'll say what the magnitude is in a second than for an electronic transition. But again, what the vibrational Stark effect or Stark spectroscopy in general gives us is the sensitivity of a vibrational frequency to an electric field. And we're going to turn this around now and use it to measure local electric fields. I should say in passing that this observation of a large difference dipole for the carotenoid in this large integral membrane protein was at the time a particularly important result because it explained why it is that historically linear shifts had been seen in response to transmembrane potential, something that had mystified biologists and physicists for many, many years, going all the way back to the early observations of what was called the carotenoid band shift in the 1950s, and is the basis of our understanding of things like the chemiosmotic hypothesis. So this turns out to be a quite important result, quite aside from stimulating what follows from our work. So we've measured the vibrational Stark effect for the first time. We were told that it was impossible to measure. It turns out it's quite easy to measure. And what we're talking about again is the difference dipole going from the lowest vibrational state to the first excited vibrational state. Um, and we've done this measurement now for a series of relevant oscillators. The ones that are most useful turn out to be carbonyl groups. Carbonyl groups are great because they have a fairly intense absorption in the infrared, and they have a fairly large difference dipole. They're a real pain to work with, unfortunately, because in the case of proteins, you have a very large background coming from the amide bands in the protein um, uh, uh, primary sequence. But we have ways using isotope substitutions to get isotope difference spectra. Let me just make a note about the numbers here. So we'll just round this off to one. So what this again means is one wave number per megavolt per centimeter. So what that says is that if I had a, let's say, carbonyl group whose difference dipole, or in this case bond dipole, because it's really the bond locally that matters, was aligned with the field, then and the field were 1 megavolt per centimeter, well, then the spectrum would shift by one wave number. And if it were locally 10 megavolts per centimeter, it would shift by 10 wave numbers. If it were 100 megavolts per centimeter, it would shift by 100 wave numbers. It's that simple, okay? It's a measure of the sensitivity of the transition to a field. It's just a very difficult thing to measure because of where it is. Nitriles are great for many reasons. They have a reasonably good extinction coefficient. The absorption, of course, for a triple bond is quite shifted to higher frequency, and the difference dipole moment is also reasonably large. Carbon deuterium, it turns out to be very useful. I'll say something about that at the end, but it's very hard to measure. Its extinction coefficient is small. By the way, IR spectra, and probably most of the people in the audience who remember their IR from introductory organic chemist, the IR people tend to talk about small, weak, strong. They use funny language like that. But there are, of course, extinction coefficients, that is, absolute measures of the absorption intensity that are available, and here they are. And the difference dipole moment for a CD bond is not bad. But again, the good thing is that it's in an uncluttered region of the spectrum. So these are especially CD and carbonyl are what we'll talk about the rest of this talk. Now, for vibrations, the polarizability change we've found, and one can compute this as well, tends to be very, very small. So it's truly a linear Stark effect. Now, you may say, well, where are these things? Well, of course, nitriles are very commonly found on many, many drugs. They're not naturally present in proteins. Carbonyl groups are everywhere in proteins and in catalysis, and very important for what we'll talk about now. And carbon deuterium can be introduced chemically. So these are found on drugs, substrates, non-canonical, modified amino acids, and I'll say more about each of these in a minute. So this is a direct spectroscopic measurement. There are some problems with it, and I don't want to get too much into the details of this because I want to focus more on catalysis. But there are limitations to this spectroscopic measurement, having to do with the fact that we have to put it in a frozen glass in order to measure things. We can't measure it in fluid solution, and yet we do most of our measurements on enzymes in solution. But it turns out there are really three separate ways, and they're relatively independent, that we can measure this probe sensitivity. One is what I just described, the vibrational Stark effect, and the good thing is we can make a parallel plate capacitor and measure. We'll call that the intrinsic delta mu, but there are these problems. The second is vibrational solvatochromism. Now, that's an experiment that's familiar to lots of people in fact, there's lots of work that happened. Alex Demchenko, for example, in Ukraine, has done a lot of work on spectral shifts of electronic transitions in solvents. You've probably all seen a dye molecule in a nonpolar solvent absorbs to the blue, and you put it into a more and more polar solvent, and it shifts to the red. Same thing applies to vibrations. It's been known for a long time, not understood or explained, and we'll show that by using simulations, we can understand it quantitatively and get out absolute values of the field without having to worry about some of the confounding factors that arise in the spectroscopic method. The problem is, and this is a big problem, is that it turns out that the way in which sulfatochromism works depends a lot on the specifics of the molecule and, of course, the whether or not molecular dynamics simulations are relevant. This is an area that we're very actively involved in. We have a whole bunch of recent papers basically showing that in order to get reasonable simulations of sulfatochromism, you need to use polarizable force fields. So this is a very time intensive simulation. And if you're interested in that, there's a paper on the archive from us just very recently and a whole series of papers that precede it arguing that that's required. The third way you can do this is to abandon experiments altogether and simply use high-level ab initio quantum chemistry to get out this difference dipole. That is, we can just apply an electric field in a computer, and we can apply it in any direction we want, and ask what is the response, and that that works really well. We use this quite a bit. Of course, not surprisingly, the answers depend a little bit on the methods that are used. And so we're working very closely with theorists using a wide range of ab initio quantum chemical methods to see what gives us the most accurate accurate result. So each of these three methods sort of has pluses and minuses, and we do them all and sort of look for convergence for the probes that we're interested in using to probe electrostatics in catalysis. Let me just illustrate sulfatochromism, because this is a familiar experiment to everybody. This is an experiment that anyone who's on this call who has access to an IR spectrometer can do in an afternoon. And it's kind of surprising, actually, if you look just at a carbonyl group. We're using acetophenone here because we can introduce acetophenone as a non-canonical amino acid in proteins. You'll see that the carbonyl group, which everybody is familiar with, is coming between 1700 wave numbers, is in the IR, is absorbing here in hexane in a nonpolar solvent. But as we go to more and more polar solvents, this spectrum shifts to the right, just like electronic transitions that have a charge transfer character shift in going to more and more polar solvents. Now, solvent polarity, of course, in fact, this is the way solvent polarity is defined by organic chemists. They use spectral shifts, but there's no units associated with that. It has no meaning. So I'd like to get, even though we use the language of nonpolar and polar, and it's useful for chemical people, it's actually a rather confusing unit. And I'd like to shift away from that and say that what we think is going on here is that the field, the electric field exerted by the solvent on this local probe, is going from relatively small in hexane to relatively large in a solvent like water, in a polar solvent like water. And what we're going and what we mean by that is that the solvent organizes itself around this functional group, and of course this could also be true at the active site of an enzyme, and it creates this field. Okay, and what you see is that the spectrum shifts to the red, but also it broadens, and the origin of that is the distribution of fields is very large in water. It's smaller in hexane. I was shocked actually at how large these fields are. We'll say a thing about them in a second, but I think the key take-home message here is that if you're close to a solvent molecule, and this carbonyl group is surrounded by these solvent molecules, the solvent, of course, is also made of electrons and protons. Those are charged particles, and though there's greater or lesser degrees of local charge separation in the solvent, that solvent exerts a large field on this local probe. And in fact, we think those fields can be organized by the solute, and this can be relevant to non-enzymatic catalysis. So this is classical solvatochromic behavior, and we interpret it using molecular dynamics simulations. So we just run a simulation in which we, allow the solvent to equilibrate around the solute, and then and at each frame, we calculate what the projection is of the field created by the solvent on the bond. And so it's just a simple classical treatment of that interaction. And that's shown in this picture on the right, which is when I first saw this, I frankly was really, really shocked. And let me just be very careful, go through it very carefully. So zero field would be what the field would be in the gas phase, where there's no solvent present. And as we get larger and larger fields, that's what's on this horizontal axis. And the numbers are negative because these are attractive interactions. And that goes back to this convention about the definition of electric fields. And these are average values because the solvent is fluctuating around, of course, in the simulation. And so we get the average value, which then would correspond in the spectrum to the peak positions here. And that's what's plotted on this axis. So this, if we just go boom, 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 take the peak positions and plot those here for each of these solvents for this carbonyl group. And here on this horizontal axis is a computed average value of the field. And what we see is remarkably over a very wide range of fields, there's a linear relationship between observed frequency and calculated average value of the field. Okay, so what's the slope of this line that fits through this? Well, it's the Stark tuning rate. It's wave numbers per megavolt per centimeter. So that's why I went through the units in such detail before. And we can then compare that with what we get from these other independent spectroscopic measurements, and we get the same result to within the approximations that are inherent in each of the methods. The other thing that's really striking about this is how large the fields are. So even in hexane, a so-called non-polar solvent, the fields are substantial. They're large. And again, hexane is made of electrons and protons, so it's maybe not surprising. But if we get to water, the fields get very, very large. Okay, and remember my original example on catalysis. You can see that even in water, the fields are large. And I'll revisit that question of why water isn't a great catalyst at the very end. Now, we get both the average value and the distribution, the moments of the distribution, and so we can get out the line widths. And it turns out we can also compute these line widths based on this simple idea of a Stark probe interacting with a solvent. So if you buy this and you're following what I'm saying, and this now is really the main point of this whole, I apologize, lengthy discussion, but I suspect this is new to most people. We observe frequencies. That's something we can do by IR spectroscopy or Raman spectroscopy. And using this essential calibration curve with simple solvents, we can extract what the field is projected onto the bond. Okay, and we're going to use that now to make connections with function in catalysts. Okay, so I'm going to go fairly quickly now, but I hope to have spent a lot of time on the background so that what I'm saying now, I can go quickly and it makes sense. So let me talk about the original experiment we did on the enzyme ketosteroid isomerase. This is now fairly old work, but it was really the experiment that convinced me that this was worth pursuing. So what's shown here is the mechanism for this enzyme. It's a very simple and frankly not the world's most interesting enzyme, but it's an enzyme that we were introduced to by a colleague here at Stanford. And as the name implies, it does something to a steroid, which is shown here. And the steroid has a carbonyl group on it, so that's the origin of ketosteroid. And the ketone engages or binds in the active site of the enzyme, binding to a functional group, a tyrosine and an aspartic acid, both hydrogen bonds, and both, as it turns out, rather short hydrogen bonds. We know from structures that these hydrogen bonds are only about 2.5 angstrom, so they're unusually short hydrogen bonds. And they turn out to be really important for what I'm going to say in a second. And the mechanism of this reaction, as the name implies, is it's an isomerase. So there's a general base here in aspartic acid, which plucks off a proton from this position, creating this dienolate intermediate, which would ordinarily not be very stable, but is stabilized in the active site of the enzyme. And then this goes on to put the proton back over here. And when that happens, the double bond has shifted from here to here. And so that's why it's called an isomerase. So it's a simple acid-base reaction involving an isomerization. So it's a simple mechanism. What's important from our point of view is to look at where the charges are moving. And what you see is there's right here at this carbonyl group, there's a movement of charge, okay? It has to be in order to go to this intermediate. And in fact, this enzyme has been extensively studied by mechanistic enzymologists. And we are just, borrowing their historical work, and the transition state lies somewhere here. So now we can go back to our picture way at the beginning and now sort of frame the question a little bit more specifically in the context of carbonyl chemistry. Of course, a carbonyl group has some degree of dipolar character, but the dipole character gets much larger going through the transition state to this intermediate and then on to products. So this is the difference dipole that we're going to be interested in. And then the question is, what is the field, or is there a field, or is it pointed in the right direction? Is it focused effectively on the carbonyl group? Okay, that's really now reframing the question now in the context of using the vibrational Stark effect to probe that field. So the key here was that there's an inhibitor for this enzyme, well known from the literature. It's 19-nortestosterone. This is a controlled substance, which we were lucky to get our hands on from our former governor, Arnold Schwarzenegger. That's the origin of his big muscles. This is an anabolic steroid. And it goes in right in the same position. But of course, in this case, the double bond has already moved, and therefore this is an inhibitor. And it's a very, very good mimic for what's going on in this reaction. And we can isotopically substitute this oxygen for oxygen 18, so we can do O18 minus O16 IR different spectra and then look at the IR transition. And we were completely astounded to see that there's a huge shift of that vibrational transition for that carbonyl group to the red in the IR spectrum. It's actually quite easy to detect because it shifts so far to the red. It's also quite narrow, which is interesting. And just for comparison, here's what the spectrum of it looks like in water. Here's what it looks like in DMSO. Here's what it looks like in hexane. So you can see this is way, way, way far to the red. So if you're following my argument here, this means that the field must be enormous projected on this bond, okay? And but and we can go much further than this because, of course, it's an enzyme, and so with an enzyme we can make mutations that affect the catalytic rate. These are all mutations that other groups had made previously to amino acids in the active site, including one of those, the tyrosine that interacts directly with the carbonyl group. And what we see is that as we make mutations that make the catalytic rate worse, so we can measure KCAT, what we see is that the spectrum shifts from that extreme red further and further to the blue. And if you're following my argument, red means big field, blue means smaller field. And so just looking at this directly, looking at the experimental result without any analysis, you can see that there's a relationship between the catalytic rate and the field, okay? And that's a new result, and it's a big deal. Now there's an argument that when you make a mutation, that these mutations are often perturbing the structure locally, and the fields are very, very sensitive to local structure. So we put in a lot of effort doing perturbations locally that are structure conserving, specifically focusing on this tyrosine, which is one of the two amino acids that is a hydrogen bond donor to that carbonyl group. So it turns out there are actually three tyrosines that are themselves fairly closely interacting. That's a whole story in itself. And we could replace each one of them individually with chlorotyrosine using the technique of amber suppression to introduce non-canonical amino acids into the active site of the protein. This more remote one, the one that's closer, and the one that's directly hydrogen bonded. And what we see is that when we do that, here's now the peak for wild type. We mutate this one, we see a relatively small shift, but a shift to the blue, a shift further to the blue if we make this one chlorotyrosine, a shift further to the blue if we make this one chlorotyrosine, and if we make a double mutation, one of the ones I just showed you, along with this one, we get a further shift to the blue. We can measure the rates for each one of these, and now these are relatively small perturbations, but we have high resolution structures that we obtain for all of these, and these are structure conserving. And so we see a systematic, again, connection between the catalytic rate and how red shifted or blue shifted these carbonyl peaks are. So now we put all of this work together, and this now is a very busy slide, but it's sort of the bottom line. What's plotted here on the vertical axis is the activation free energy obtained from transition state theory. So, and we can argue whether that's the best approach to use, but we're using that approach. So we take the measured catalytic rate, and many of these measurements came from other people, but they were carefully done, and we repeated them, and they were very accurately done, and we added a few ourselves. So we have the catalytic rate, and we get out the activation free energy using transition state theory. That's what's plotted on this axis, the vertical axis. So these would be a low transitions, a low activation free energy would be a fast enzyme, and a slow enzyme would be one that has a high activation free energy. And then what's plotted on this axis is now the experimental observations that I just showed you. So these experiments and these experiments, now with the peak positions interpreted through the calibration curve, the solvatochromic calibration curves, and the vibrational Stark spectral calibration curves that I described before. So interpreting those shifts as electric fields projected on that bond. So this is now a rigorous physical, physically interpretable metric for what the field is, obtained experimentally, but interpreted through simulations. And what we see remarkably is a linear relationship between activation free energy, which is after all an exponential axis, and the projected fields over an enormous range of fields. And notice how big the fields are we're talking about here. We're talking about huge electric fields at the active site of this enzyme. So what does this mean? This is what a physical organic chemist would call a linear free energy relationship, and many of you have probably seen linear free energy relationships in other contexts, but invariably the horizontal axis is calibrated relative to some standard reaction, and then given the name of whoever it is, Bronsted or some other person who came up with the standard reaction. This is now an absolute scale, which is coming from physics. So this is something which you can calculate from first principles. So this is a true linear free energy relationship. Now, the linearity here is remarkable, and it allows us, we take this line, and then we can do something that we can't do experimentally, which is we can imagine what would the activation free energy be if we simply turned off electrostatics, something we can't do that experimentally. So we just extrapolate this to zero, and the answer is we would get 18.4. This is now in kilocalories per mole. And we know what the activation free energy for this reaction is in solution by the same mechanism. We know what the activation free energy is in the wild type enzyme. And so what this tells us is how large is the electrostatic contribution to catalysis? And we see that at 18.4 kilocalories per mole, this is about 70% of the activation free energy, which is due to electrostatics. So what I started my talk with, which was this hypothetical picture that maybe the field from the protein has something to do with catalysis, we now have, I think, a quantitative demonstration that it's not a small thing, it's a big thing. It's actually a very, very important contribution. It's not what you find now. It's just creeping in now into textbooks. It's not what you find in most biochemistry or chemistry textbooks. You find things about orientation, local effective molarity, local organization. Of course, all those things are important. They're not irrelevant, but they are there to create this large electric field. So that's really the bottom line of this discussion. Okay, so that's an old result. Now let me bring up to much more recent results. So if you look at that picture, this is just the same linear free energy picture I showed you a second ago. You might ask the question, well, can we get an enzyme that's better than wild type? That would mean a lower activation free energy still. Would that mean an even larger magnitude of the field? In other words, is this line something that we could imagine extending further? And the answer to that question, of course, was we didn't know. And it wasn't really clear how to ask that question using ketosteroid isomerase. What you really want is you want an enzyme that you can do, let's say, directed evolution or some other maybe computational approach to connecting the activation free energy or the catalytic rate with evolution. We spent quite a bit of time looking at the beta lactamases. This turns out to be a very complicated story. Beta lactamases are involved in antibiotic resistance and have been extensively studied since the introduction of penicillin many years ago. We have a whole clinical history of the evolution of the beta lactamases. It's a complicated story. We've published actually quite a bit on this. This was the first paper, and then there are several subsequent papers, and I'm not going to talk about that because it's a little bit complicated. And instead, we were working with a completely different, again, classical enzyme widely studied by mechanistic enzymologists, which is liver alcohol dehydrogenase. And we were looking at something completely different and stumbled into an example of exactly what I'm showing you here. So let me quickly say a little bit about liver alcohol dehydrogenase. So, and this is an area we're still very actively working on. So everything I'm saying is a little bit preliminary. This catalyzes the reversible hydride transfer reaction between an alcohol and a cofactor producing an aldehyde. And of course, this is something that we're all familiar with because we drink alcohol. So this side reaction produces some of the side effects of drinking. And this enzyme is a classical enzyme been studied by many people for many years. And the active site is, again, a carbonyl group. We're going to be looking at the reverse reaction here because that's going to be our probe, starting with an aldehyde. And the aldehyde we're going to look at is a very, very slow substrate, which is essentially an inhibitor, which is CXF. And this will both be our inhibitor and our probe, where we replace this carbon with a carbon 13. And the mechanism here has been extensively studied, involves hydride transfer from this cofactor, from this very specific hydrogen to that carbon center. So again, it involves carbonyl chemistry, not unlike what we talked about with KSI. And again, not unlike KSI, this carbonyl group interacts with two local functional groups. One is a serine 48, again, a hydrogen bond. And this is what motivated our original work, a zinc ion. There are zinc ions at the active sites of many enzymes, and this is one example. There are other relevant amino acids in the environment, but we're not going to talk about those today. We'll just focus on the serine and zinc. Here's the active site structure is sort of flipped upside down, so I apologize for that. So here's the serine coming in, and here's the zinc, and there's that carbonyl group. This is a structure that we obtained. This is a fairly high resolution. And so you can see these local interactions with that carbonyl group that are going to be responsible for creating the local fields, just like those amino acids at the active site um, of KSI. So we're going to probe the field again. So we do exactly the same thing as before. We look at solvatochromism. We get one of these field frequency calibration curves. I don't need to go through this again. We put the carbonyl group into the active site of the enzyme. And once again, remarkably, we see this very large shift to the red, not quite as far to the red as it was for KSI. And again, very narrow. I should emphasize that this very narrow characteristic of IR bands and Raman bands, for that matter, in proteins is well known. There would be no spectroscopy, IR or Raman spectroscopy in proteins if it weren't for the fact that bands are relatively narrow. And the origin of that isn't clear. Presumably, it has something to do with the fact that unlike a simple solvent where the molecules can jump around, here the molecules are much more constrained in their motion. At least that's probably what we think is going on. That's still a speculation, something we're interested in better understanding. Okay, so there's a big field again at the active site of this enzyme, and it's created presumably by these interactions. So the first thing we did was to replace the zinc ion with cobalt. This is something that had been done many, many years ago. We had to develop a new method. This, by the way, was done by in part by Ji, who is the person who introduced me to Stefan, which is why I'm presenting this today. So this was an important connection. And this is something we're trying to model actually with Stefan's group using MOFs. So we replaced zinc with cobalt or cadmium. These have both been done a long time ago. We had to improve the methods. And what we observed was when we introduced cobalt, we were really surprised. The band that was already very red shifted further to the red. Okay, so if you're following my argument, that means the field's even larger in the cobalt enzyme than in the wild type enzyme, something we hadn't had a way to look at in the case of KSI. And then we measure the rate, and we use, in this case, the reduction of acetone as a surrogate for the reaction. And what we see is that replacement of the zinc by cadmium, which causes very little shift in the IR spectrum, also creates very little change in the rate. This is just the initial velocity. And on the other hand, with the cobalt enzyme, we see a very large change in the rate. It's much, much faster. Okay, so bigger field, faster rate. Okay, so that's an interesting result. And these are structure conserving. Okay, and here we have X-ray structures of all of these. We then mutated the serine, and in the case of serine, the only really easy mutation to make is serine to threonine, and or get rid of the hydroxyl group altogether. Let's talk about that first. Get rid of the hydroxyl group altogether. Not surprisingly, you'd expect the field to be smaller because the hydrogen bond creates the field. And indeed, the spectrum shifts to the blue. And if we measure the rate gets slower, just as you would expect, just now taking IR spectra as a way of predicting rates. But to our surprise, and this is something we're very actively looking at right now, and I can say some speculation if you're interested, but we're trying to understand why this mutation makes this redshift. It also makes the rate faster, okay? So S48T, threonine, makes the rate faster. S48A makes it slower. So we can go either way now, okay? So we begin to reconstruct now through these changes in metal and changes in local amino acids a plot not unlike what I showed you for KSI a minute ago. In fact, these all fall on a single line. Okay, so it's again one of these linear free energy relationships, either making it worse than wild type or, interestingly, make it better than wild type. And now the question is, if I were to, let's say, put cobalt in to the S48A mutation, would that rescue this? In other words, this makes it faster, this makes it slower. If I combine them, would this bring me down here? Or for that matter, if I took this mutation and combined it with this change in metal, would that combination move me still further down on this line? Or for that matter, would things stay? I'm sorry, I don't want to give away the story here. Would that make things even further even faster, lower the activation free energy further. And of course, we did those experiments. We got structures for all of them. And indeed, if you add up this and this change, you would predict if this linear free energy relationship between activation free energy and field holds, that that combination would shift you here. And indeed, you find that the rate is the activation free energy is faster. And can we rescue? Yes, the cobalt can rescue the effect of S48A. It doesn't make it as good as wild type, but it makes it a faster enzyme. And so now we have all these points on this curve. Again, both much slower and much faster, and combinations. These effects are additive. Okay, and if we look at the actual rates of the reaction, we see now wild type looks like a terrible enzyme. Here we have something that, if we combine things, is much, much, much faster than wild type. So this is really an important observation, because we can make things both faster and slower than wild type, and it suggests a general strategy. To design a better enzyme, you need to design a larger field. And it really gives an underlying basis for the design of catalysts in general, whether they are biological catalysts or, I would argue, any catalyst. Okay, this is a general result. We think we're still looking, obviously, at more and more examples to find when this doesn't work. Now, I think in the interest of time, I'm not going to say anything about, I see my time is running out. Let me just very, very quickly say something about sort of where we're headed with this. And I think if I summarize this maybe with just this one slide, it'll give you a suggestion. I've been focusing on the projection of the field on the carbonyl group. We're again using classical electrostatics, but it's always the dot product of the field with the reaction difference dipole, which is happening here. But fields are three-dimensional, and the question is, how do the fields in 3 dimensions matter, or do they matter? Are they catalytically relevant in any sense? Especially in the case of hydride transfer enzymes, it's interesting to know whether there's fields relevant along the hydride transfer axis, because that, after all, is a movement of charge. And in principle, the way we can get at that is by introducing additional probes. In the case of the aldehyde, it's fairly simple. We can introduce a probe that's not quite orthogonal. It's at roughly 120 degrees to the carbonyl group, which is a carbon-deuterium bond, and we can use that as a vibrational Stark probe, and we have. And I'm just going to skip the result. That's just sort of a statement of what we can do. And finally, we can go into the 3rd dimension, because in the case of, let's say, these cofactors, we can introduce stereospecifically a deuterium here in the place of hydrogen. And we've done quite a bit of work on this. This is actually a paper that's now published, looking at the carbon-deuterium stretch in the cofactor in anticipation of measuring the fields, in that case, in the case of LADH and another enzyme we're working with, in one direction, 2 directions, and then in this essentially orthogonal direction. Obviously, they're not perfectly orthogonal. They're whatever the enzyme gives us, but we really have the potential to probe the fields in 3 dimensions and understand whether these, what the full scope is of the field dependence. So that's really where we're at right now, trying to work this forward. Let me just sum up by going back to the slide I introduced very early on, sort of the important conceptual slide, which is electrostatic complementarity is the usual way people think about electrostatics. Here we're talking about electrostatic activation. I hope I've convinced you that electric fields are directly related to catalysis. It goes further than that. It's reactivity in general. The local fields matter. And in fact, again, the connection with Stefan, wrote a really important paper in JACS in now, I guess, almost 4 years ago. Gosh, it seems like just last year, applying this concept to covalent drug design. It's an area we're very actively working on now. So we think this is a very general principle. And it all comes back to this original diagram that I showed you at the beginning. Now, yet another version of it with a different set of colors, but it really shows the movement of charge associated with the reaction, lowering the activation free energy and the presence of the field due to the enzyme, not an external field, but the local fields due to the active site organization of the enzyme. And so just to summarize, the vibrational frequencies are sensitive and local probes of electric fields through the vibrational Stark effect, the thing that started all of this and was our original entree into this. We then turn it around and calibrate our Stark tuning rates by sylvanochromism and simulations to get at absolute fields, or we have other approaches, as I briefly mentioned. I showed you an application to KSI where we could get out the absolute contribution of catalysis of electrostatic fields to catalysis at the active site. And then in the case of LADH, we have both a metal and a hydrogen bond donor, and their effects are not unlike what we saw in KSI, interestingly, also for the metal. And the electric fields are additive and predictive, and bigger fields give lower activation energies and faster rates. And so we made an enzyme which is much, much better than the naturally evolved enzyme, which is interesting. And so this then we think is a general design principle, and there are people now trying to implement this in the context of a catalyst design. And that's not mostly our work, but it'll be the work of others. So just to quickly finish up, here's a slide with some of the important players. This is the most important person really at the beginning of this, graduate student Stephen Fried, who is now a professor at Johns Hopkins working with postdoc Sayam Bachi, who's now at Pune in India. Yufan Wu was a graduate student. She's now a postdoc at Harvard. Here is Zhe, who is very familiar to Stefan, working with Chu Zhang. So my two fantastic students, both from Tsinghua University, who worked on the LADH problem. Importantly, we're not X-ray crystallographers, but we've done a lot of X-ray structures working with a key collaborator, a staff scientist at SLAC, who is a master crystallographer, Matthews. And then the two-dimensional stuff, which I didn't talk about in any great detail, has been done in collaboration with Tom Markland, postdoc of his, who's now an independent faculty member and a computational person, a former postdoc of mine, who's now just got a professorship in Germany, Jacek Kosic, another Stephen Fried, though I have had two Stephen Fried. This is Stephen D. Fried II, who's a graduate student in my lab now, working closely with a current postdoc, Srijit Mukherjee, who's also working with Stefan on the MOF project. So with that, I think I'll stop. I'm sorry I went a little bit late. I hope I went through enough detail that you could get a good flavor of what I'm talking about. I'll be glad to take questions. Thank you.
Thank you very much. Very nice presentation, amazing lecture. Dear colleagues, yes, Stefan, please. You would like to ask? Oh, no, no. Okay.
He's just clapping.
Okay. Yes. Some questions? Okay.
No, may I ask a question?
Sure.
Yeah. Hello. Thank you very much for the brilliant lecture. I have maybe not a question, but just to clarify for myself. No, computational electrostatics for biomolecules, for molecules usually is focused on drawing these red, white, blue pictures like you have shown on the slide, where we draw the molecular surface and color it with respect to the value of electrostatic potential.
Correct.
And if I understand correctly, actually for a lot of applications, especially for catalysis, we should also look at the gradient of this potential to the
Exactly.
So we need, roughly speaking, to draw the same surface, but in terms of E instead of potential.
Correct. That's right. That it's the gradient of the potential gives the field. Again, taking a completely classical view. You're exactly correct. So the red, white, and blue. I mean, actually, it was the red, white, and blue. So Barry Honig was the person who first introduced these red, white, and blue pictures. Of course, an American, very patriotic colors. And really, the question that started all of this was, how red is red, how blue is blue. Um, uh, and so much of our early work was just attempting to map these fields and relate them back to the electrostatic potential maps that Barry had introduced. I mean, those maps are very useful, but they don't give you very quantitative information because there's red and very red, and there's blue and very blue, and the question is how much, and as you say, what are the gradients of that field or of that potential. And so that's what then led to what we're describing.
Mm, okay, maybe have you met Nathan Baker as that person? Yeah.
I'm sorry.
Did you mean Nathan Baker as that person who introduced red, white, blue pictures?
I think of it as Barry Honig and Kim Sharp. I mean, I think those were at least for me, the standard, algorithms that are used to generate those pictures, which you find in any paper on X-ray structures of a protein, at least for me, were first introduced by Barry Honig, but
Yeah, yeah.
maybe other people had done it. I mean, Barry Honig at Columbia University.
Okay, thank you very much.
Thank you. Stefan?
Yes, Steve, thank you for the nice presentation. You're speaking about deep pulse. I always like to think about electron density. Everything is connected by electron densities and how this is moved from one point to another point. This we need to control. And you showed how important the electric field is. My question is, do you think we can apply this knowledge in real? I mean, with MOS, we just bit try, but I mean to design catalysts that also be able to distribute this electron density or the dipoles is quite challenging. What you think about, would be this possible in the future? Also to use this knowledge to speed up, to make ammoniac synthesis at room temperature, or
Yeah.
to basically bring it to the
So, yeah, well, the answer is, of course, that's the dream, because that's what chemists would like to do. If you look in the literature, you'll find all sorts of examples where people have found interesting effects of local charges and counterions and things of that sort. And it's the idea that solvent polarity, going back to that language, matters in chemistry is obviously not a new concept. The question is, what is it exactly about the solvent that's responsible? Of course, in an enzyme, I mean, I've always taken the somewhat odd attitude, or expressed the somewhat odd attitude, that proteins are really much simpler than simple solvents because, of course, we know where every atom is. Okay, and including water, often water molecules, which are organized in the active sites of enzymes. So in some ways, proteins are easier than, let's say, uh, the general area of heterogeneous catalysis. But there are lots and lots of speculation out there about the roles of local electrostatics. It's just that there hasn't been a way of actually probing it. What people do, of course, is change screening, change the local polarity or the ionic strength of the media, and they see effects. And the question is, what's really going on? And it would seem that, what's really needed are local quantitative probes. And I think that's what we've introduced. So if you look, I mean, since the first introduction of the vibrational stark effect, which is now quite a long time ago, um, over the last 5 years or so, there have been extensive work by many, many groups, especially electrochemists looking at electrically active surfaces, trying to characterize the fields. Again, lots of historical speculation about the fields in the double layer near electrodes. And now there's some really quantitative information on that coming from a wide range of groups. Um, last year, I guess late last year, there's an issue of Chemical Reviews that was edited by myself and Teresa Head Gordon at UC Berkeley, who's a theorist who's responsible for much of the theoretical work that I didn't discuss today related to KSI. Um, and that there are several very lengthy reviews on the use, trying to characterize the effects of electric fields on reactions, and in some cases experimentally using the vibrational Stark effect. Um, and of course, there's also a large, I mean, I have a slide. Okay, let me show you this slide because this maybe addresses your question.
Yes.
A matter of perspective. So there's a lot of work, there are lots of papers being published now on, mostly by theorists, on the effects of external electric fields on
Hmm.
chemical reactions. And the there's a problem with most of those papers, and the problem is that they use atomic units. I don't hope there are not too many theorists on this call. They may object to this. Atomic units are great. The trouble is that they sort of disguise the truth. Okay, and that is it's very hard to apply a very large electric field externally, anything close to the fields that we're observing locally due to, let's say, hydrogen bond interactions. And what's shown here are a couple of examples. So here's just a parallel plate capacitor. And you can't get much above a megavolt per centimeter applied field without getting dielectric breakdown. Okay, essentially getting electrochemistry and then lightning going through the sample. There are some very interesting effects, which are, I would say, interesting but not very well understood, of uh, external field effects. So this is, Stefan, where you can actually tune the field by changing changing the potential that's applied. Let's say at an STM tip. This is a paper that
Hmm.
everyone quotes in Nature, but the field wasn't known in this. They don't have a probe. In principle, if one could do, and there are some groups trying to look locally at vibrations on the substrate molecules in such an experiment. In principle, you could get out information on the local fields. There's some interesting work at Columbia. This is still ongoing, again using an STM tip with molecules just freely floating by, and isomerization reactions or bond dissociation reactions being affected by field. So this isn't really design. This is, something where you just turn a knob, which is pretty interesting. Design is a much more complicated problem because you need to position every atom exactly. Just to finish this story, of course, we're all familiar with field effect transistor. That's an example of a field, okay, affecting conductivity, and the transmembrane potential, which is important in neuroscience and in bioenergetics, the field created across a membrane. And that's, again, something you can change by changing the ionic strength, sort of analogous to what's going on here. But the actual fields inside here are not known. We're trying to actually to measure those right now. Now, going to the next step, and let's say doing what David Baker or Don Hilvert does and trying to, from first principles, design enzymes specifically, has been a very, very challenging subject. There's just I think last week a very important paper coming from the combined Baker and Hilvert lab on designing enzymes that are actually competitive with native enzymes. Most of them are not. Most of the ones that have been designed in the past are pretty lousy. And then people do directed evolution, which gets you somewhat better, but it's sort of a black box. You don't know what happened. It's not a chemically satisfying approach, at least not satisfying to me. So the question is, can one do this really by design? And we're not going to be the ones doing that. It's going to be people like David Baker, then incorporating electric fields into their design algorithms. And as far as I know, that has not yet been done. I know of several groups that are trying to do it, computational groups. And, if that proves to be successful and not just sort of empirical discovery like what happened with LADH for us, then that would be exactly the answer to your question. It would be possible. So, I mean, moths, zeolites, there are all sorts of structured frameworks where you can imagine decorating, charges in specific ways or functional, polar groups that could play an important role in electrostatic catalysis. And we'll see. We'll see. There's, I think, already a body of work out there that could be interpreted that way, but the question is design, prediction.
And but Steve, honestly speaking, that's why I wanted to hear your opinion. Yes, I know, and I could imagine for MOF more than for zeolite, but imagine is one thing. The thing is to doing, and as we work together on this, I understand the immense challenge, also scientific challenge, how to control this. And we did. Let's say for what we imagine later to make enzyme catalysis in a MOF pore, we just did two functional group, and this was already challenging. So, but as
Yes.
so I really see what have to be done. I would like to go in the direction, but it's really immense of effort or synthetic effort to design a material like this. It's not, yeah, it's a really hard nut.
Yeah, well, no, I mean, since what, 80% of all industrial chemicals are made using catalysts, this is of huge, global importance. And so, yeah, and it's largely empirical. I mean, shake and bake. People throw things together, and of course, they also change as a function of time. And so, again, enzymes are in some ways a little bit simpler. An enzyme pretty much, functions now. I mean, either if it stops functions, it's because it denatures or something like that. But if you have let's say, a nanoparticle or something like that whose surface is constantly reconstructing, well, that's quite a different problem. And so, yeah, it's an interest, and it's a really important challenge. We've sort of come into this quite by accident because we were really interested we were really interested in this problem right here, the bioenergetics problem.
Hmm.
And we're now coming back to that problem.
Super.
People know that transmembrane potential, I mean, you're thinking everything about ion conductivity and so on through ion channels is being regulated by these potentials. And so knowing what they are locally is really, really important, but it's largely speculation.
Okay. I don't see more questions. Okay, maybe time to finish our seminar. Stephen, thanks again for amazing lecture in chemistry, physics, biochemistry. It's a aggregation of several scientists. Thank you very much.
They're all related. Yes. Okay. Yeah. Well, and I hope things get better in Ukraine. That's our wish for the world. The world is a
Yeah.
sad place right now.
And maybe for the students that listen, don't be shy to write Steve if you have any question or want things like this. He will be for sure answer. So don't be shy to, even if it's a big name, but he's nice and always will answer your email. So because also students are here and they vote in the things from. So I just encourage, if it's okay, Steve, to write you if they have any question
Sure.
or everybody.
Oh, yeah.
Glad
Yes.
to. Glad to. Okay. Have a good evening. I have a whole day ahead of myself. Okay.
Have a nice day, Steve.
Okay.
Thank you. It was
Bye-bye.
amazing to
Yeah.
listen your lecture.
Thank you. Bye-bye.
Bye.